You know, electric motors are literally everywhere. They're the invisible workhorses powering our entire world, from the massive pumps in our city's water systems to, well, the tiny thing that makes your phone vibrate. They're always on, working behind the scenes. But what happens when they just stop?
Well, the stakes are unbelievably high. As the Electric Power Research Institute, or EPR, makes really clear, when a critical motor goes down, it's not just some mechanical hiccup, it's a financial disaster. We're talking about lost production, huge repair bills, the whole 9 yards. And the key to preventing that failure? Well, that journey starts way before the motor's even bolted to the floor.
And that journey starts right here, with sizing. This is all about picking the absolute right motor for the job. And there's this really common temptation to just go big, to think more power is always the answer. But as we're about to see, that's almost always the wrong move.
So how do the pros get it right? Well, according to the experts, it really boils down to a 3-step science. First, you have to analyze the load. What is this motor actually moving? Is it a conveyor belt, a fan, a pump? Then you do the math. You calculate the big 3: inertia, torque, and speed. Only after you have those precise numbers can you go out and find the perfect motor for the job.
Let's just zoom in on torque for a second. In simple terms, it's just the twisting force the motor needs to produce, and it's always fighting against 2 things. There's a constant load. Think of it like friction or gravity, something that's always there. And then there's a temporary load that only pops up when you're trying to speed things up. Nailing this calculation is just absolutely essential.
Okay, so that leads to a really interesting question, right? If this is all just math and physics, a straight-up science, why are so many motors out there way too big for what they're actually doing?
Well, it turns out the reasons are usually pretty practical, even if they're not exactly efficient. An engineer might build in some just-in-case power for future production goals. Or they might just be playing it super safe, to handle any weird load changes. And then there's my favorite. A motor fails, and the maintenance crew, in a hurry, just grabs the next size up off the shelf to get the line running again. It happens all the time.
But here's the kicker. That bigger motor comes with a hidden cost. A cost you pay every single day it's running. This gets us to the real cost of a motor. It's not the price on the invoice. It's the electricity it eats up over its entire lifetime. And that cost never, ever stops.
And this is where the big trade-off happens. Look, a standard efficiency motor, it's cheaper to buy for sure. But an energy-efficient one? Yeah, it costs more up front, but it sips electricity instead of guzzling it. And that's not all. The research shows they run cooler, which means they live longer, and they're way better at handling overloads. So the bottom line is that higher sticker price can actually save you a ton of money in the long run.
Okay, so let's say the worst happens. Despite your best efforts, a motor fails. Now you've got a huge decision to make. Do you try to repair it, a process called rewinding, or do you just scrap it and buy a new one?
And you've got to be really careful here. To rewind a motor, a repair shop has to bake it in an oven to burn off all the old, fried wiring. But if they get impatient and crank the heat up too high to save time, they can literally cook the motor's core, causing permanent, irreversible damage. That motor will never be as efficient again. So a cheap, rushed repair can end up costing you a fortune in wasted energy.
All right, now that we've talked about what you can do to prevent these issues, let's play detective. Let's look at what actually goes wrong inside a motor. Thanks to some really detailed industry reports, we have a surprisingly clear picture of a motor's weakest links.
And this chart just says it all. I mean, look at these numbers from EPR's data. A whopping 41% of all motor failures are because of the bearings. Another 36% are tied to the stator, which is basically the copper windings. You add those 2 up, and you're looking at over 3/4 of all failures coming from just 2 parts of the motor. It's incredible.
And this right here, this is the rotor. It's the part that actually spins. You can see it's a pretty beefy, solid piece of equipment. But even this tough guy isn't invincible. It still accounts for almost 1 out of every 10 failures.
So if bearings are the #1 problem, the answer's simple, right? Just pump them full of grease. Well, not so fast. This is one of my favorite mythbusters from the EPRI guide. It turns out that forcing too much grease into a bearing can make it overheat and fail just as fast as not having enough. In this case, more is definitely not better.
Now here's the good news in all of this. Motors almost never die silently. They give you warnings. They send out distress signals. And the 2 biggest ones you can spot are way too much vibration and way too much heat. If you walk by a motor and it's shaking or it's hot to the touch, it's basically screaming for help.
And that idea, that motors give us warnings, leads us right into the modern way of thinking about maintenance. The goal is to stop being a firefighter, constantly reacting to emergencies, and start being more like a doctor, predicting and preventing problems before they ever happen.
And this is your game plan for how to do it. If you feel that vibration, you do a vibration analysis to check for bearing wear before it gets critical. If a motor feels hot, you check the current to see if it's being overloaded. Simple, proactive tests for things like insulation resistance or even just checking the color of the oil can spot problems way before they lead to a total breakdown. This isn't just about fixing things. It's about being smart and saving a ton of money and headaches. And that brings us to the final, really big picture question. We've seen how much efficiency matters in the long run and how much failure can cost you. So what's the smarter strategy? Do you play whack-a-mole, replacing motors one by one as they die? Or do you make a bold, proactive move? Do a group upgrade to high-efficiency models and lock in all those future energy savings right now? It's the classic short-term cost versus long-term gain dilemma, and it's a question every single plant manager has to wrestle with.